So we mentioned last class that the particles in a gas don't all have the same speed, and there's actually a distribution of speeds. So we can look at the rate of incidence versus the speed v. So this is the number of molecules that actually have that speed. And the actual experimental shape is something like this. So it kind of looks a bit like a parabola, and then it cuts out and drops back down to zero. There's sort of an exponential decay there. And we're looking for this function f. It's a probability distribution function. And what it'll tell us is at speed v, the area will tell us the probability. It'll be f of v, and then the width here is dv. It's centered on the speed v, and the height, the value of that function, just tells us the probability density. Then we multiply by dv, and we actually get the probability. And it's the area of that rectangle. So we're looking for this function f. And again, f tells us, so we can highlight this, f tells us the probability of finding a speed in the small range from v to v plus dv. So I guess actually I haven't really labeled that properly. If it's from v to v plus dv, then I should really move, there we go, the v coordinate over, because it's the start of that rectangle and not the midpoint of that rectangle. Okay, so what can we say about this function? Well, the total probability is 1, so that means the area under this curve has to be 1. So when we integrate over all possible speeds, our function f of v dv, we have to get 1. And that's just, probability distribution functions have to satisfy that. Another condition is, from the equipartition theorem, if we find the average kinetic energy. Now, the way to find an average value is by taking that quantity and then multiplying by the probability density at that point. And so this is sort of saying how many molecules are at that speed. So weighting it by the probability is going to give you the average value of half mv squared. Now we know that by the equipartition theorem, is going to be 3/2 kt. Now another bit of notation for this, we use these angled brackets here for the average values. This is going to be the average value of the kinetic energy. The average value of anything, the average value of some quantity g, you would put g in here and integrate g f of v dv, integrate the probability density. So those are two conditions that our probability distribution has to satisfy. So let's think about what functional form it has to have here. Well, it's got to depend on the magnitude of the velocity, i.e. on the speed, and not on the direction, because, if we have, a velocity of 100 meters per second that way and 100 meters per second that way, those two situations have to be equally likely. So it depends on speed and not on velocity. What else can we say? Well, it has to treat the components x, y, and z equally for sort of the same reason, right? So this particle's moving in the z direction, let's say, and this particle's moving in the y direction, let's say. Sort of our right-handed three-dimensional coordinate system. And these two, again, need to be equally likely. So the function for the x direction sort of has to be the same as it is for the z direction. And this leads us to conclude that the function has to be something like e to the minus v squared times some constant, because that can be split up into a function for the x direction, a function for the y direction, and a function for the z direction that are all the same. If this was proportional to v, that wouldn't work, because v would be a square root, and then you couldn't split it up in that way. But if it's proportional to an exponential of minus v squared, then it can be split up in that way. So it's reasonable to say that our function must be something like an exponential of minus bv squared. Now, there's more to it than that, because for any velocity v, there's a number of x, y, and z combinations that will give you that velocity. And all those combinations are going to lie in a spherical shell. And the volume of that spherical shell depends on the size of v. So as you go faster, the spherical shell gets larger, and then there's more x, y, and z combinations that could be allowed. So the volume of this shell is a surface area times the thickness. And the surface area of a sphere is 4 pi v squared dv. So you see that as velocity increases, the surface area gets bigger, the volume of the shell gets bigger, and that means there's more possible states, i.e. the probability is going to increase. So, if we put those two things together, then the function has to depend on both v squared and this decaying exponential. So that means that our function is going to be, well, some constant times v squared times e to the minus beta v squared, where beta is another constant. About this functional form is if you actually graph it, then you find something that agrees with the experimental curve. It's sort of quadratic here at low speeds and then decaying exponential here at larger speeds. So that's good news. The other thing is that this functional form agrees with our normalization conditions. We know that the total probability has to equal 1. And this was going to help us find the value of alpha and beta. And then this has got to be 3/2 kt when we integrate alpha v squared e to the minus beta v squared times 1/2 n v squared dv. Now both of these are significant integration challenges, and we'll talk about those in class a little bit. This one is perhaps the easier of the two, but it still means we have to do a calculus 3 integral, which is e to the minus x squared. Let's see how that one works out. It turns out that this is the result. So this is the probability density function, or the probability distribution function, and it's known as the Maxwell-Boltzmann function, the Maxwell-Boltzmann distribution. It tells us the probability density and the actual probability, again, we get by multiplying f of v by dv. And it depends on the mass of the particle, the temperature, to a certain exponent, and then this exponent here, remember, is supposed to be proportional to v squared. It ends up being mv squared over 2 kt, which is interesting because mv squared over 2, that's an energy, and so is kt. So this is energy over energy. It is dimensionless. And we get a lot of that sort of thing in physics. There's another distribution that we had in this course, which is the Planck distribution. And you'll recall that was something like e to the minus hf is an energy, over kt is another energy. And that appeared in the Planck distribution function. So we have seen something like that before. So I suppose this is another factor that leads us to be confident in this functional relationship for the Maxwell-Boltzmann distribution function. So when we meet in class, we're going to explore this a little bit. We're going to integrate it to make sure it satisfies the normalization conditions. And then we're going to numerically integrate it in a few different problems to find out, say, the probability that the velocity lies in a certain range from here to here. Another problem we'll look at is what's this velocity right here? I guess we could call that the most common velocity. And we'll apply it to several different gases as well. But this is our main result for today. It's known as the Maxwell-Boltzmann distribution function.